In tutorial 1, we looked at how to set up basic DC simulation for basic DC resistive circuits. In this tutorial, we will be looking at how to set up AC simulations. The first thing that we need to do when setting up an AC simulation is deciding what frequency we will be working at. We can change this later on, but we need to understand how the frequencies of simulation are selected in Microwave Office. Let's therefore double-click on Project Options. You can see here that you can choose a start, a stop and a step frequency, and this will create the frequency range over which you want to simulate. This is very useful if you're trying to work out a frequency response of a circuit, but in our case we just want to see a sinusoidal steady-state response. So we want to have one single excitation of one specific frequency, and we will assume that all the excitations within the circuits that we look at will be at that very same frequency, i.e. we will be in a sinusoidal steady state. To do this, firstly we need to select the units of our frequency, let's say kilohertz, and then we decide what frequency we want to work at, let's say 1 kilohertz. We tick the box which says single point, and then we must have replace selected and click on apply. The list of frequencies at which we are simulating now should appear here under current range. And you can see we've only got one of the value of 1. In terms of the units, those will be the units shown in the data entry units box. The other thing that we may want to do is to change our global units. So again, within the project options window, we can go to the global units tab, and you can see that we can pick whatever we want for our units. For the frequency, we've chosen kilohertz, so that's what we're going down to. And then resistance is in ohms. Conductance is in Siemens, although often enough you'll find that it's easier to have it in millisiemens. In our case it won't matter. Inductance is in nanohenries, capacitance in microfarads. We could have it down to nanofarads for instance, which may be more useful. Voltage is in volts, current is in milliamps. In terms of the units of length, we won't be using this in our tutorial. You can also see the power can be expressed both in a linear and a logarithmic form. If we wanted the power expressed in a linear scale, at the moment this would be in milliwatts, but you can select anything else. And if we wanted it expressed in a logarithmic scale, it would be in dBm. Now click on OK. So what we set in our project options was the units of our components and also the frequency of operation, which was, as you may recall, 1 kilohertz. Now we can open our schematic diagram, just the same way as we did for our DC circuit. Right-click on Circuit Schematics, select New Schematic, and then type in a name. Again, a blank schematic canvas opens up, and on here you can add whatever elements you wish. To add a new element, you know that you can use the Elements tab down here, but you also know that I don't particularly like to do that. I just press Ctrl L, and then a full list of elements available opens up. You can search by name, and at the moment this is what this is set to, because the funnel is up here, but you can also keep the Ctrl key pressed, and then click on the heading description at the same time. And the funnel now changes to description, which means that you can search for an element by description. Once you're familiar with the simulator, you'll find it easier to search by name because you know the acronym that is used. However, for now, you probably find it easier to use the description. First thing, we need to have a source. So I want an AC voltage source. And you can see that one has already come up, which is called ACVS. This is just what we'll get. So double click and then a single click to place. Now if we want a ground, we can get the ground from up here, or we can simply press Ctrl G and then place the ground like so. You can see that in terms of the parameters of your signal generators, which you may change, you've got magnitude of course, angle, which is the initial phase, and offset, which allows us to have a DC component for our sinusoid. In this particular tutorial, we will leave everything pretty much the same. One thing, however, that is not there at all is the frequency. So how do we set that? Well, this is a quirk of the simulator which you have to be very aware of. The frequency is set globally. So the frequency of this signal generator and any other AC signal source will be set by the project options. So here we set 1 kHz. This property will be inherited by our AC generator, which will also operate at 1 kHz. Now we want a load that we can connect to our ideal voltage source. Again, we press Ctrl L, we type our ES and our resistor should come up, and then we just place it. We can connect the two together with the wiring tool. Remember that all you have to do is hover over the terminals of one of your elements, click, and then hover over the other terminal that you want to connect it to and click again. Now let's change the value of our resistor to something a bit higher. Let's say 50 ohms, which, as you may have realized, is one of my favorite values. If we want to make the circuit bigger, as big as it can be for the window which we have available, we can simply click on this icon up here, which says View All, as you hover over it. If we click on that, you can see that now the simulator has maximized the size of the circuit from a visual point of view based on the window that is got available. Now the thing is, before we added annotations, you remember we simply right-click on the circuit schematic and went on to add annotation. However, in this particular instance, annotations wouldn't be terribly useful because we're not working at DC and we know that voltage and current have got an average of 0. That is, if they don't have any offset. In this particular case, we haven't got an offset because we decided not to have any DC component, so voltage and current over a period would average to 0. So how do we see them? Well, we have to set up graphs that allow us to see the time-varying waveforms of this circuit. To do so, we simply go onto the Project tab yet again, and we right-click on Graphs. Then we select New Graph. It will be a rectangular graph, and we call it AC voltage and current, and click on Create. You see now a new graph has appeared, and we want to add some measurements to it so we can see our voltage and current waveforms. In order to display current and voltage waveforms, we must have some measuring elements in our circuit. So if we go back to our schematic, what we can add to this schematic is simply a voltmeter and an ammeter to measure current and voltage. To do so, simply press Ctrl L, and then you want a voltage meter, which is already there. It's called V_meter, and you place it across the terminals of the resistor and connect it like so. We also want to measure the current that goes through the resistor, and to do so we need to have an ammeter in series with the resistance. Let's delete this wire here by simply clicking on it and then pressing delete. Now we press Ctrl L again, and this time we find a current meter and we place it like so. We connect it with the wiring tool to the rest of the circuit, and now what we've got is the same circuit as before, but we have a means of measuring current and voltage. Bear in mind that these elements have no effect on the operation of the circuit, since your current meter has got 0 resistance and your voltmeter has got infinite resistance, so it's not drawing any current at all, thereby not affecting the operation of the circuit. So now we need to go back to our graph. We can do so either by clicking up here. You can see that here you've got a tab-like profile, and this allows you to switch between schematics and graphs really quite easily. Or we can simply go down to the Project tab on the left-hand side and double-click on the graph, and this would also get it to display. Now, to add a new measurement, we simply right-click and then select Add a new measurement. This window opens up, which may be slightly confusing. Don't be confused by the AC linear measurement. This is not what you are looking for. You need to look at non-linear measurements to see the time waveform of periodic signals. So you can just collapse this and then expand your nonlinear measurement section, and here we'll select current as the measurement type, and as the measurement we'll select one which is called I-time, and this will give you the time domain current profile. The other thing that we need to select is the schematic from which this measurement will come. In this case we only have one schematic, but normally under here you would have a list, and you'd have to select the appropriate data source name. In this case, as I mentioned, we have one schematic, and hence this would be really quite easy. We have no choice. Then you have to pick the measurement component. You are trying to measure the current, the time varying current, but in a complex schematic this may be measured in various different points. So, to find the right point in the circuit, click on this little square with 3 dots. This will open your schematic diagrams, and you can select what element you want to use to measure the quantity that you've specified. In this case, we've specified the current in the time domain, so what we want is a current meter. We click on that, and then we click on OK, and then Apply. Next, we want to have a look at the voltage, which is also under the nonlinear heading right down here. So we select voltage as the measurement type, and then we scroll down and select V-time as the actual measurement. Yet again, we need to specify the data source name, which is already there and is correct, and then click on the 3 dots, and this time we'll select V-meter as our measurement tool, and then click OK. Then Apply. Now we've added all the measurements that we wanted to add to our graph, and hence we can simply click on OK. Now we will simulate. Now we've got current and voltage displayed on our graph, but the problem is, of course, that current and voltage have got very different magnitudes and different units. So is there a way to display them on the same graph, but to make the waveforms be as large as they can possibly be, so as to visualize them better? Yes, there is indeed a way. We simply need to right-click on the graph and then go to Properties. We then select the Measurement tab, and here we can decide which measurement is associated with each vertical axis. We've got a left vertical axis and a right vertical axis, and we can make use of both. Now, for the current, we could have the left axis, and for the voltage, the right axis. How do we do that? We simply click on the measurement that we want, the voltage. This is currently associated with the left axis. We simply click on right, and this will associate our measurement with the right axis. Now, if we want to verify that this has worked, let's click again on the current measurement, and we can see that goes onto the left axis, and then on the voltage measurement, and we can see that that goes onto the right axis. And then click on Apply, and OK. First of all, look at the legend. You can see that now I-time is associated with the left axis, which is indicated by the letter L. V-time is associated with the right axis, which is indicated by the letter R. The problem that we have is that because they are associated with 2 different axes, they've been both maximized, they are perfectly in phase, and hence they are overlapping. So you can't distinguish between the two. Those are the right waveforms, on two different axes, on two different vertical axes, but they are superimposed upon one another. Is there a way to avoid this sort of thing so that we can still see them as distinct? There most certainly is. We simply right-click on the graph, go to Properties yet again, but this time we choose the Axis tab. Now for the x-axis we can keep the auto limits. For the left axis, which is the one associated with the current, we can untick the auto limits box, and then instead of having a current between -20 and 20 milliamps, we can simply choose -25 to 25 milliamps and then click on Apply and OK. Now we can see the two waveforms as distinct. So to recap, remember that on your legend you can see a lot of useful information. I time is associated with the left axis and is expressed in milliamp. V time is associated with the right axis and it is expressed in volts. Of course, these are the units that you selected in the project options under the Global Units tab. Lastly, for this tutorial, I would like to show you a different way to carry out your measurements, which is a little bit more compact, but also a lot more prone to error. But for completeness, I will show you all the same. Let's go back to our schematic. Now, let's click on this little icon up here. And as we hover over, this will say Measurement Probe. So we click on the Measurement Probe icon and then we place it on one of the terminals of the resistor. First word of caution, a measurement probe can only be placed on the terminal of an element. For example, you can't have it here. If you did, the simulator would generate an error. You must always have it on a green square or a green circle. So let's move it back to the circle. Now what we can also do is get rid of these two elements here, our ammeter and our voltmeter, and reconnect the circuit. We can use the measurement probe to measure voltage, current, and even power. So if we go back to our graph, we now need to modify our measurements to tell the simulator to go and have a look at what the measurement probe has rather than the voltmeter or the current meter, because we've removed those. So let's right-click on the graph. We'll have to do this for both. Go on to Modify Measurement. Let's start with I time. And then we click on the three dots. And this time we select our measurement probe. And click OK. And then OK again. Then we have to do the same for the other measurement. So we right-click, go on to Modify Measurement, select V time, and again click on the three dots to select the measurement component, click on M probe, and then OK. And then OK again. Now let's simulate. You can see that we got exactly the same result. So you may be wondering, well, why complicate the circuit by having to insert a voltmeter and a current meter? There are very good reasons for it. Firstly, current. Suppose that you have this sort of arrangement and you put your measurement probe right there. What current do you think that this is going to give you? That is a node which has got currents coming in and going out of it. So which current are you going to get? The simulator will have its own way of deciding which one is going to give you, but it is much better to have a current meter in the right branch to make sure that the current that you're measuring is the one that you want. The other problem is the reference for your voltage measurement. In this particular case, it's quite straightforward because we've got ground on one of the terminals of the resistor. So it is very obvious how the voltage is being measured. But suppose that you had a network of this type and that you wanted to measure the voltage across this resistor. If you put an M probe there, it'll either give you the voltage between this point and that point, or this point and this point. So the easiest way to get the right measurement for the voltage in this particular case would be to simply source a voltage meter and put it across the terminals of your resistor. Now you know for certain what voltage it is that you are measuring. So amp probes are useful, but I think that it'd be much better for you to use voltmeters and current meters for now. This concludes our first tutorial on AC circuits.